One way that we can model the motion of an object is through motion diagrams. You can think of these as being like images that were created using a strobe light. So we get flashes of light at regular intervals that are going to illuminate some object and let us know where it is at that moment in time. We'll also include some additional information there. We'll use arrows to show the velocity, both the direction and the amount of velocity, and arrows to show the acceleration. If this shows our object at 5 different moments in time, but equally spaced in the amount of time, we can surmise a few things here. First off, this shows roughly equal spacings between the dots, which means that the dot or the object must be traveling at about the same speed the whole way through. Now we can also show that using arrows to illustrate velocity. Since the velocity is constant, the velocity arrows are going to all be the same size all the way through. Then we turn our attention to acceleration. In this case, acceleration would be 0 because the velocity is constant. I'll just show that using dots instead of arrows down at the bottom. So this is a complete motion diagram now for an object that is traveling at a constant velocity. Now let's look at something a little more complicated, say an object that's speeding up, maybe a car that's starting at rest and gradually speeding up after, say, the light at an intersection turns green. If we think back to just the position of the dots, originally we had these evenly spaced. So a certain amount of time goes by and we travel a certain distance. That same amount of time goes by, we travel the same distance. But for an object that's speeding up from a slow speed, that won't be true. Initially, it's not going to cover very much distance in that first time interval, but it's going to speed up. So the second time interval, it covers a little more distance. The third one, it covers a little more distance. This arrangement does a better job of showing that relationship. Small distances at the beginning on the left side, and large distances at the end on the right side. Now we're also going to show this using arrows for velocity and for acceleration. So for my velocity arrows, I'm going to start out with, it's a velocity always to the right here, but it's going pretty slow initially. So a little arrow to begin with, and then as time goes by, these arrows are going to get bigger until they get to their biggest at the far right side there. Now acceleration on this one is a little bit tricky. We just have acceleration. That by itself is a little bit tricky. We on these diagrams are not going to do much with the size of the arrows or the amount of acceleration that we have here, just because we haven't dealt with that concept yet, what the quantity of acceleration means. So instead, all we're going to do here is indicate a direction for acceleration. The rule that we need to keep in mind here is that if an object is speeding up, and we don't want to say if an object is accelerating to mean speeding up, because in physics, accelerating could mean slowing down. It could also mean changing directions. So if an object is speeding up, that means that velocity and acceleration are in the same direction, or at least they have a component that are in the same direction. We may have two-dimensional motion that gets a little more complicated, but for now, with one-dimensional motion, it means they are in the same direction. This object is speeding up, it's moving to the right, so that must mean that acceleration is to the right as well. Now if we consider this set of positions, we'll again think of the motion as being left to right here, and just from the positions at different times we can get an idea of the motion. Again, we have some areas where there are large distances traveled in that time interval, other areas where it's a small distance traveled. When the dots are farther apart, when it's a larger distance traveled, that indicates that it's a larger velocity. So we can fill in the velocity vectors, the velocity arrows right now. we're going to have a big arrow over on the left side and gradually gets smaller and smaller and smaller as we go by. Now as for acceleration on this one, our object now is slowing down. That means that velocity and acceleration must be in opposite directions. So we're going to have our acceleration pointing to the left when velocity points to the right. Now let's consider this case where we'll say we have our object starting right here, and it's going to be moving to the right, and then it's going to turn around and move right back along the same path, but if we do all the dots right on top of each other, we won't be able to see what's going on. So I just have it shifted down a little bit here, but then it goes and moves back to the left. So now let's think about the velocity and acceleration for this thing. Initially, we have big spaces between our first couple of dots. That tells us we have a big velocity there. It's moving to the right initially, so we're going to have a big arrow pointing to the right for velocity. And then that spacing is decreasing as we go to the right, so we have a smaller, maybe not quite that small, but a smaller arrow anyway, going to the right. And a little smaller, a little smaller, a little smaller. And at this point it is going to stop altogether for just an instant before it turns around, goes slowly to begin with, and then a little faster, a little faster, and a little faster, and a little faster all the way back to the beginning. Now let's think about acceleration. When the object is moving to the right, it's slowing down. Anytime we have an object that's slowing down, velocity and acceleration are in opposite directions. So I can put those arrows pointing to the left, opposite the rightward motion here. And then for this other section, our object is going to be speeding up as it moves to the left here. So that means that our acceleration vectors need to be in the same direction as our velocity vectors, which is to the left still. So we'll still have these leftward arrows all the way through. So we have acceleration that does not change direction, even though the motion or the velocity does change direction in this case. Good example of something like this would be throwing a ball upward. As that ball moves upward, it's slowing down because gravity is trying to pull it downward. When it gets to its highest point, it turns around and starts to fall again. And as it falls, it speeds up again because gravity is pulling it downward. So it's got a constant downward acceleration. Its upward velocity decreases until it stops, and then it starts to have a downward velocity, which begins very small. It gets to be a larger downward velocity by the time it gets to the bottom of its path. That description that I just gave would be an adequate narrative description for the motion of that ball. There's a lot we can do with these motion diagrams, but keep in mind these are just one way to model motion, one of many that we're working with, and one skill that we'll need to develop is how to take a motion diagram and go to some of those other descriptions, other models, or vice versa, take one of those other models and go to a motion diagram.